What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and this week we are going to do part 2 of the design Dropbox system design question. We're going to take it to a little bit more of an advanced area this week. We're going to talk all about the different kinds of compression that Dropbox uses when they're uploading and sending all of a user's files. And we're also going to talk about the sync engine as well as the actual, the way they store their files in the Dropbox architecture. I'm going to go super in depth into a bunch of the components of the Dropbox system, and I want everybody to watch this video with the concept that these are all different possible tools that you can add to your toolbox and pick up as you need in a systems design interview. These are different things that, although they're specific to Dropbox in this case, you can add to any system design question and talk about with your interviewer. These are things that, across all companies, people are using these sorts of, tools and algorithms to basically solve similar problems, because although every company does something super different and every system designs question is going to be slightly different, there are some really common basic threads that you'll pick up across different system architectures. So think about this in two ways. One, it's interesting. It's really cool to think about how a company like Dropbox is doing some of these, pretty complex maneuvers with an enormous amount of data, which is a problem that a lot of people solve in the software industry. And then secondly, think about it again as the different ways in which you can augment any system design, where you can add a load balancer or data replication or erasure coding. That's going to be something cool we talk about today. So if everybody's ready, let's get into it. Okay, let's go over the problem just in case you missed last week's video. But if you did, I highly suggest you go back and check that out. Not that it's a prerequisite for this video, but it's a good video if I do say so myself. Design a system such as Dropbox or Google Docs in which a user can store their data on remote servers in the cloud. The remote servers should store files durably and securely, and these files should be accessible anywhere with an internet connection. The user should be able to make changes to files locally and have the changes be automatically reflected in the cloud and on other clients. So, this is something I think everybody uses a tool like Dropbox or Google Docs. It's almost like a given these days, but once upon a time, this was a brand new concept. So let's talk about what kind of goes into a system that can accomplish these things. I want to go over just briefly the system design recap, the kind of steps that you want to take when you're designing a system. The first thing will be to scope the problem. The second thing will be capacity estimation. The third thing, and again, a few of these steps you can kind of do in different orders, but there's the database design, the system APIs, the core algorithm, and finally, load balancing and caching. So last week we talked a lot about database design. Today we're going to talk a lot about core algorithms. So what core algorithms are we going to talk about? Because of course, in a system, there are many core algorithms often. So today we're going to talk about Nucleus, which is Dropbox's sync engine. They actually did a rewrite of their entire sync engine, and they wrote a ton of articles about it, which have been super, super interesting and fascinating. So I highly suggest you check out Dropbox's, content that they put out about their systems. And the second thing we're going to talk about is Magic Pocket, which is Dropbox's storage system, the thing that actually stores a user's files. So let's talk about the sync engine first. And here are some requirements that we have to check these boxes if we're designing the sync engine of Dropbox. So their sync engine, we have to store files durably and securely, right? And we talked about this again a lot last week. Files have to be able to be uploaded, updated, deleted, and downloaded. The files and folders sync across multiple devices from anywhere with an internet connection. So this is the big piece of the sync engine. And the system should support offline editing, that the user should be able to update their files, add, remove, delete, and be synchronized across all of their machines and be able to be accessible from anywhere, regardless of whether they were edited offline. Once a user comes back online, that has to be synced across all of the devices. So the unique challenges at Dropbox when it came time to build this sync engine, and this is a really good exercise with any system design question. You want to ask yourself, what are the actual unique challenges in this system? Because that's where you can really impress your interviewer and build a system that's not generic. It's not that it works in general. It really works for not only technically, but in a business way, right? Like this is something that actually solves the unique challenges for the company's customers. And this is a really good exercise because it kind of gives you these guideposts or these guiding lights where to understand where your system has to go, where it has to fit within, rather than coming with a system that you've already, taken out of the box and you're just like, oh, here's the system. No, these are the things that it really changes an entire interview when you can understand and appreciate the unique challenges, and you can build a system that accounts for them and works well within those unique challenges. So some of the unique challenges at Dropbox. File sync is a unique distributed systems problem because Dropbox clients are allowed to go offline for long periods of time and then are expected to reconcile the changes on return to the network. So this is a unique problem, right? I have to be able to have different clients that are not all online at the same time and might come online with different changes. And the sync engine has to be able to reconcile all of those changes in a way that makes sense to the user. The user can't go online and be like, hey, why did this get overwritten by this other thing? And then, some developer at Dropbox is like, well, the sync engine reconciles it in this strange way. No, it needs to be able to reconcile them in a way that makes sense to everybody. So this is a pretty unique challenge because to reconcile changes that are happening not online all at once, there's an endless possibility of potential, things to reconcile. So it's a very interesting problem, and we'll talk more about how Dropbox goes about, actually building a system that can do this. Dropbox aims to just work on any user's computer, regardless of their config. They support Mac OS, Windows, and Linux, and each has a variety of file systems, all with slightly different behavior. Guaranteeing durability in this environment is difficult. So everybody kind of takes this for granted that, oh, I have a Mac, I'm running Linux, I have a Windows machine, Dropbox should just work. The file systems are all totally different or slightly different on all of those machines with a lot of different like hairy, things. Everyone has kind of been the person who's like, well, it worked on my machine. This is like, compounded. It's supposed to work on any machine. So this is an interesting, unique challenge at Dropbox. Testing sync engines well is challenging because the number of possible combinations of file states and user actions is astronomical. This is interesting, and it kind of ties into the first point about reconciling changes. Theoretically, there's all different sorts of changes that a user can make on all of their machines, on all of their files. And to actually test for every case is very hard. It's almost exponential, the amount of different states that a user's files can be in. So we'll talk more about how Dropbox solves this, but it's a very interesting problem to solve. Unlike a lot of other problems that we solve with software where there's a, is the user logged in? Yes, no. Those are two states versus this kind of exponentially, growing possible combinations of states that anyone might have at any given point. It is often hard to precisely define correct behavior for a sync engine. So this again ties back into that first point. It's hard to say what is the correct sync behavior. What should happen to two changes? How should they be reconciled? And how can we reconcile them in a way that the user expects and is not surprised by? It's not black and white. It's kind of, arbitrary to a certain extent. So this is something that the Dropbox engineers had to think about and iterate on. So let's talk about an example of, reconciling changes. So in this scenario, what is the correct behavior? So here we have it's a, what might happen if someone is trying to change things in their Dropbox folder. So here we have a shared folder, and it's called initial, and we see Alberto moves archives to January. So he moves this archives folder into the January folder. So you can see that here, right? Archives is moved to the January folder. Beatrice, who also has access to this, file state, moves drafts to archives. So she puts drafts, this folder, into archives. And why can they both do this? Maybe one of them is offline and they both have this initial copy. This is what it looks like on their machines offline, and they make changes and then they come online, and somehow the Dropbox sync engine has to reconcile those changes. And you can see all of a sudden you have this circular dependency, right? In Beatrice's version, drafts is a part of archives. But in Alberto's version, archives is a part of drafts. So what do you do? So if we apply these moves directly, we have a cycle in our file system graph. It doesn't really work. You can't apply both of the changes. Archives is the parent of drafts in Beatrice's case, and January is the parent of archives, and it's a child of drafts in Alberto's case. And that is a cycle in the graph, if everybody remembers from our graph series. And that won't work in a file system. So what is the correct final state in this situation? So the old system that Dropbox used to use would have basically duplicated each directory, merging Alberto's and Beatrice's directory trees. So they would basically have two versions, right? They'd have a version of drafts that holds January, or a version of archives that holds drafts, and then with Alberto's changes, there would be a copy of drafts that holds a copy of January and archives. So you'd end up with both. Nucleus, which is the new sync engine of Dropbox, actually just keeps the original directories, and the final order depends on which sync engine uploads their move first. So whichever one happens first, that's the one it keeps. So, this is an interesting example, but it's a very simple example, right? This is just 3 folders and 2 moves, and Nucleus has this satisfying final state. But this is literally like small potatoes, right? How do you create a sync engine without drowning in the corner cases, the edge cases of all of these potential, moves that you could make? So let's just see finally. This is the sync engine classic. As I said, it just ends up copying and duplicating, so it can kind of do both at the same time. And then with Nucleus, it just takes whatever happens first. So we'll talk about more how they actually, solve these problems and how they avoid these, corner cases. But I want to take a brief moment to go on a sort of small tangent on whether or not a code base should be rewritten or not, because this was one of the things that in the articles, in the research I've done, Dropbox called out, that they had to do a rewrite, but they waited a really long time to do the rewrite. And it was a great piece on when to do a rewrite and when not to do a rewrite. And this is not totally relevant to system design. It's not really totally relevant to interviews either. But I think that these are kind of some of the ways in which a developer can think that is obvious to an interviewer, that an interviewee is thinking about these things. And it's a very good sign for an interviewer when a candidate is actually able to talk about things in this way. It kind of shows that you have some experience. So I want to go into this brief tangent of to rewrite or not rewrite. And this is a rewrite checklist. Some of the things you need to ask yourself before you do a big system rewrite. The first question: have you exhausted incremental improvements? Have you tried refactoring the code into better modules? Have you tried to just change what you have and make what you have better and easier to reason about? Have you tried improving performance by optimizing hotspots? This kind of means, have you, are there certain ways the system is being loaded down, and have you specifically targeted those, pain points and tried to make them better? Can you deliver incremental value? Is there a possible scenario in which, if you did this in an incremental way rather than a total rewrite way, can you still deliver value with each incremental change? So these are some of the questions you'd want to ask yourself before you do a rewrite. Finally, can you pull off a rewrite? Can you even do it, right? Do you deeply understand and respect the current system? I thought this was such a great point in the article I was reading, because often people are rewriting systems because they don't understand them and they don't respect them. And they're like, well, I don't understand that, so I'm just going to rewrite it myself. That's often very damaging because you end up with a system with different problems and you lose track of the problems that the original system was solving. So this is a really important piece. Do you really know your system inside and out so that when you do the rewrite, you can make sure you don't end up in a different bad spot? So often software teams, they'll just rewrite something and it's not actually better, it's just different. And that is a waste of everybody's time. So this was a really good point. Do you have the engineering hours? Do you actually have, the time to spend rewriting something? Can you accept a slower rate of feature development? This is an obvious one, right? Because when you're rewriting stuff, you're not developing new features necessarily. So your company has to be okay with this slower rate of feature development. And then, do you know what you're going towards? Why will it be better the second time? What are you trying to accomplish that the first system is not accomplishing now? And what are your principles for the new system? What are the things that you are rewriting for? What are the things that you can't accomplish with the old system that you are trying to accomplish with the new system? So this was just kind of a brief tangent, but I thought it was very interesting. And again, this way of thinking is a really, really strong indicator for me as an interviewer that a candidate is a mature engineer. They're thinking about, how does software engineering actually work in practice rather than just in concept? Because I think a lot of software engineers at the onset of their career, they kind of come at problems as if they have infinite resources, time, bandwidth, people, and that's never the case in real life. Often you kind of have to be asking yourself these questions before you can just, we'll just rewrite it. So I thought this was a really great, something to kind of a little bit of a thought piece as, when you're thinking about systems designs, these are the things that you want to also be aware of. Let's get back to the sync engine. So how does the Dropbox sync engine work, and what were the specific things that they changed when they did this major rewrite from the classic sync engine to Nucleus? Of course, it's a really complex system, and I'm not going to go so in depth about, the various pieces of it, but I'll talk briefly about kind of the key points and the key takeaways of what they were trying to accomplish and how they changed that from the classic sync engine to the Nucleus sync engine, which they use today. So classic sync to Nucleus. The first thing they did was they had a better, stricter data model. And this is something I think you'll see often in software engineering, that it's difficult to write good code if the data model is not well defined and thought out. And it's easier to write good code on top of a really strong foundation of a good data layer or a data model. How is the data modeled in the system? And then how can our code interact with it in a way that we want, in a way that makes sense? So they took a data model that was a little bit flexible, something that often happens, I think, at the beginning of a company because you don't really know where you're going. And they kind of honed in on some key pieces and recreated a data model that would embody the principles that they were trying to accomplish with this new sync engine. It was designed for testability. They went into this rewrite having in mind that they would need to be able to test things really, really well because of the enormous amount of corner cases that Dropbox encounters. This was something that was really important to them. Rather than have something go out in production and have bugs reported and have that be the testing, we all have been there. They needed to be able to test a lot of different things before they released anything. So file system states or all these kinds of, different conflicts that could come up when syncing and merging, reconciling changes, that sort of thing. So they also have these coarse-grained locks that are held for longer periods of time. Now, what is a lock? In case you don't know, a lock is when you're accessing something in a database, and so, or in a data layer, and nothing else can also access that piece of data at the same time. It's locked in that state until whatever process or thread has finished with it. So that way, instead of having multiple things happening at the same time on the same data, it actually happens sequentially, and it has to happen sequentially. So because they did this, they sacrificed parallelism in order to make this system easier to reason about. Often people are like, asynchronous, parallel, multiple threads, great. But in this case, they actually sacrificed that in order to have the data be easier to reason about and be more consistent, so that the same thing happened to the data over and over and over again, because it was all sequential. It wasn't, sometimes it was in this order, sometimes it was in that order, sometimes it was at the same time, that sort of thing. They wrote it in Rust, which is a cool, I don't know if it's up and coming. I don't think you can call it up and coming anymore. It's come already, but it's definitely like a hot language right now. And they chose Rust because of its performance and its focus on correctness. So Rust it compiles before you are running it anywhere. And it has a very strong type system. So they were able to encode complex invariants about the system in the type system. And then they could know that it would work when it compiled and didn't error out. So that was a huge win for them, because it was a way for the language to do some of this heavy lifting for them. The language would enforce certain things about the data model, certain things about the way the system works. And again, because it's compiled, they could compile it, and if there were errors, they'd know at the compile stage rather than at the run stage when it's already on a client's machine. It runs on a single thread, the control thread, and it uses Rust's futures library to schedule many concurrent actions on the single thread. So again, this is similar to what we were talking about before, that there were some sacrifices made they sacrificed some parallelism in order to have this single thread to have things happen sequentially rather than all at the same time. And this was important to them because it's easier for an engineer to work on something that's, there's one thread that's managing things, rather than these kind of, you never know what might be accessing the same data at the same time. The control thread is designed to be entirely deterministic when its inputs are fixed, aka given a particular input, the sync engine will always produce the same output. That's the concept of deterministic in computer science. Given the same input, you'll always be sure to get the same output. And that creates a system that's very easily testable, because when given the same input, it's going to produce the same output. This allows them the ability to seed random initial file system state and other system perturbations. It's a great word, right? During testing to better cover corner cases. So they can kind of use a process to randomly generate some file system states and actually test them and know that anytime that's the state that a user is encountering, it's going to have the same exact end result because it's deterministic. And this is one of the benefits of having this single thread rather than multiple threads, is that you can kind of know exactly what's going to happen. The client-server protocol was redesigned to have strong consistency. The protocol guarantees the server and client have the same view of the remote file system before considering a mutation. Shared folders and files have globally unique identifiers, and clients never observe them in transiently duplicated or missing states. So this was a new thing introduced with Nucleus from the classic sync engine, that there's a globally unique identifier of all folders, and it won't even entertain the idea of a change or a mutation or an update if everyone's not already on the same page. So again, this is a little bit, you're sacrificing the ability for everyone to have access to the same thing at once if they can't get the same copy all at once. So that's something that they had to trade, and it's paying off for them. It's a good trade, even though they had to make that trade. So these are some of the things that how the sync engine works. Again, I'm not going to go so deep into it because it's very complex, but I want to talk more about another way that they drastically improved the sync engine, which was they changed what they were actually uploading and downloading from people's machines. So one of the ways that the way they used to do things is people would make files, they would have folders, whatever, they'd get uploaded, and it would be uncompressed. And it would maybe get compressed in S3, I don't remember, but it would basically go from the user's machine in a certain state, and it would get sent straight to the Dropbox remote servers. In this Nucleus rewrite, they made a huge performance win because they introduced a layer of compression before it gets to the Dropbox servers. So before it leaves your machine, it's actually already being compressed. And I thought it was a really interesting actual way of compressing. So let's get into it. So they're using Huffman encoding. What is Huffman encoding? First, let's talk about ASCII, right? So ASCII, when these are just, encodings for the letters and numbers and whatever, 8 bits are used for every character. So you might have, let's say, so this is a constant number of bits per character. So the character A, you have the decimal representation of that, which is 65, and the bit, as you can see, is 100, blah blah blah. And B is 66, etc. And every single letter will have 8 bits somehow, and it's a kind of uniform way of just encoding things in bits and sending characters in an encoding. So let's take an example, hello world. It's a length of 18, counting the space. That's how many characters there are. So that would be 11 times 8, right? Because there are 8 bits per character. So there's a total of 88 bits required to store the string hello world in ASCII encoding. So what's Huffman encoding? Huffman encoding is a variable amount of bits for each character, determined based on the frequency of the character in the file. So what does that mean? Rather than use the same encoding always for the same characters, Huffman encoding looks at the frequency of the character in the file, and it encodes based on those frequencies, so that if there's a lot of A's, it will encode it with a smaller amount of bits than if there are, not as many B's. And that might be, if there's not that many B's, it will use a larger amount of bits to represent it because it's going to have to represent it less often. So that's super cool. Number one, that it's not the same amount of bits for every character. And number two, you have to have this Huffman table or a Huffman encoding, to know exactly how things are being encoded for this particular file. Every file might be encoded differently. So let's take an example here, hello world. So here we have our little table here. We have all of our characters and the amount of times they appear in the string. So this is pretty self-explanatory, right? So how would you go about Huffman encoding this string? So the first thing you do, and again, I hope you all, go check out our videos on trees and graphs and all of that fun stuff, but this is a little bit of a throwback to that. The first thing you do is you create a bunch of nodes. We're going to make a tree. It's a Huffman tree. And all of the leaf nodes are going to be all of these letters. And underneath, I have all of the frequencies. So here that is. So here are all of our leaf nodes here. And it's all of these letters, right? So this is R and it has a frequency of 1, right? And this is L, it has a frequency of 3. So, and here's space, it has frequency of 1. So that's all that is. And what Huffman encoding says is that basically you call union. Again, go check out our malware video, series on all about calling union and all that stuff. But you basically you join together all of the two minimum nodes. So the nodes with the lowest frequencies. So at first we have a bunch that are the same, so that's just going to look the same. So first we're going to call union on them, right? And what we do is we create this parent, and it's not exactly calling union on them, by the way, because we're not joining them together, we're joining them to this other node, but whatever. So we join them together and we add a node in, which is just the addition of their two frequencies. So now this is 2, right? And now this is 2. So we're just, again, joining together minimums, which we have a bunch of the same. So we're going to do it for each of them. So we have another 2. We have another 2. Okay, so now we have this, small subtree, which has a parent of 2, this small subtree, which has a parent of 2. These are still lone nodes, 3 and 2. And then here is another subtree with a parent of 2. So to join together minimums, again, so our lowest things to join would be 2 2s at this point. So I'm just going to do that here. So I'm going to join together this 2 and this 2 and add them together, and we get 4. Again, there are two lowest frequencies now. It's still 2 and 2, so let's do it again. We have a 4 right here. And then our next lowest is going to be a 3 and a 4. So we join those together and we get a 7. And finally, the only two we have left is 7 and 4, so we join it together and we get 11. Okay, so now we have this kind of Huffman tree, right? So what do we do with it to get the encoding? So according to the Huffman encoding, you basically assign the bit 0 to any left branch and the bit 1 to any right branch. And you'll see how we then use that code. We use the tree to get the encodings for each of these letters. So I'm just going to do that really quick. So that's going to be 0 and 1. This is also going to be 0 and 1. And again, this is just, we're assigning zeros to the left branch and ones to the right branch. Again, we have a 0 and a 1, another 0 and another 1, another 0 and another 1, another 0 and another 1, and finally another 0 and another 1. Okay, so now we have this beautiful tree. What do we do with it? So to get the encoding for each letter, all you do is you start from the root node and you follow down the branch until you get to the letter. So let's just do that really quick for all of these letters. Let's start with H. So H is down here. So if we start at 11, the coding would be 0, 0, 1, 0. And there we have it. And then for E, the coding would be 0, 0, 1, 1. And then for L, it would be 0, 1. And for O, it would be 1, 0, and so on and so forth. You can fill in the rest exactly as described. So as you can see, what that does is the letters that appear more frequently in the string take up less bits because we're going to have to represent them more often. So what are the total number of bits for each letter here? So for that, all you do is you take the number of bits multiplied by the frequency. So in this case, it would be 1 times 4, so that's 4. Same for E. We're going to have 3 L's, so it's going to be 3 times 2, so that's 6. O is 2 times 2, which is 4, etc., etc. And finally, you add them all together, and we get a total number of bits per this string is 32, compared to the 88 bits that would have been required to encode this with ASCII. So this is something that I found really interesting, and it's one of the ways Dropbox has drastically cut down on how much time and how much stuff they're transferring over the wire back and forth between users' machines and remote servers. Okay, enough about the sync engine. Let's talk about the storage system of Dropbox, the actual system that is responsible for storing a user's data, files, whatever, in the remote servers of Dropbox. So this system is called Magic Pocket at Dropbox, and I'm basically just going to kind of give a brief overview of the different components of this system. Again, this is really useful kind of because it's interesting, but also because these components can be mixed and matched in all different sorts of ways for any systems design question. So I think this is really valuable to kind of see these different components here and think about how they could be used in other systems as well. So Dropbox's storage system. It's made up of this immutable block storage. It stores encrypted chunks of files up to 4 megabytes in size, and once a block is written to the system, it never changes. So that's what immutable means, that once it's written, it stays that way, and any updates are they're represented as additions to the file rather than modifying the original block. The workload of this system is, pretty hefty, right? It has to store a lot of data. This data has a high degree of temporal locality. What does that mean? It's just a fancy way of basically saying that the data is accessed very frequently within about an hour of being uploaded, and then increasingly less frequently afterwards. Why is this important? Because often with storage, we talk about things that are kind of hot storage, something that you're going to need to access relatively, frequently, versus cold storage, something that can be, stored away because we're not accessing it as frequently. So in Dropbox's system, what they've found is often, the file has to be accessed a lot within a certain time period, and then increasingly less frequently as time goes on. So that makes sense in general, just with files and how users use this sort of system. So what did they do? They built this on spinning media, which is hard drives, versus SSD, or I think solid state drive, that's what that stands for, which is used for databases and caches. So spinning media is good for this sort of, hot storage kind of situation versus something that is more of a cold storage that's being accessed less frequently and is therefore stored in a different way. Hard drives are durable, cheap, storage dense, and low latency. So that's what that looks like. It's, I think people have seen hard drives before, but that's what they're using in this system. So what about durability here? So the data is erasure coded. What is erasure coding? It's a method of data protection in which data is broken into fragments, expanded and encoded with redundant data pieces, and stored across a set of different locations or storage media. So with erasure coding, often what's happening is there's some kind of expansion and replication of the data. And there are these things called, I think, parity blocks or parity segments, something like that. And essentially, if there's a problem accessing the data as was originally intended, right? I want a certain block of data and something is funky with that piece of data for whatever reason. If something is erasure coded, the code can use the different fragments combined with the parity fragments and basically reconstruct the original block just in case there's some sort of issue with the original block itself. There's a wide degree of replication across multiple geographic regions. So they're replicating this data all over the place just in case an entire data center goes down or something along those lines. So let's talk about the data model of the Magic Pocket system. So here you can see we have a file, and even though the file is 8.1 megabytes, it's broken up into these blocks. It's broken up into block 1, which is 4 megabytes, block 2, which is 4 megabytes, and then this block 3, which is just the remainder, whatever didn't fit in those first 2 blocks. So first, it's compressed and encrypted, and then passed to Magic Pocket for storage. The 4 megabyte blocks are aggregated into 1 gigabyte logical storage containers called buckets. So basically, that's taking all these different blocks, and they're not necessarily related, they're not necessarily part of the same file, but it's aggregating them into these things called buckets so that they can then be used in this way and replicated, etc., in kind of a larger logical container. Buckets are then further aggregated and erasure coded for storage. So that's what we were just talking about, right? A volume refers to one or more buckets replicated onto a set of physical storage nodes. So a volume will be the bucket replicated. So I have a nice little picture here. So here's our block, right? And here's our bucket, which might contain many blocks. And then we have this volume, which is actually just the bucket over and over and over again. It's replicated and erasure coded. So there's some redundancy in the data, again, just in case there's something wrong with the original bucket, right? So just in case you can't access it, the volume has access to a replication of it or a way to reconstruct the bucket as it was. So let's talk about the architecture of Magic Pocket. So here's a great little picture. So here's a zone. Generally, we talk about availability zones. This is across a region or, some other kind of way of, grouping a certain set of nodes together. And you can see it's made up of a few different components. We have some front ends, these block indexes, and these cells. And we're going to talk about the cells in greater detail, but let's talk about the bigger components just right now off the bat. So the front ends. The front ends are the nodes that accept storage requests from outside the system. And they determine where a block should be stored and issue the commands to read or write a block. So this is kind of like the interface to the rest of the Dropbox architecture that before anything is stored, it goes through the front end, and that's what determines where and what should happen to that block. There are also cells, which are self-contained logical storage clusters. These are the actual places that the data is stored. So we're going to talk about these in greater detail in a second. And then there's this block index, which is the service that maps each block to the bucket where it's stored. So this is just, I believe, like a MySQL database or a cluster. You can see there are a bunch of them here. And this is just keeping track of which bucket, which bucket a block belongs to, so that the front ends can talk to the block index and know where and how to get or put the data into the cells. So let's talk about the cells themselves. So the cells are also made up of a few different components here. You can see we have the master, the replication table, the volume managers, and these storage devices. So let's talk about each piece of these. The object storage devices, so these are down here, the OSDs, are the actual storage boxes full of the disks that store the data. So this is actually where the data is being stored. The replication table maps each logical bucket to the volume and OSDs that bucket is stored on. So again, this is a similar idea with the block index. This is the MySQL database or cluster that's keeping track of who and where and what. So when something is coming into a cell, it knows where it's looking or where it's putting something. Then we have the master, which is kind of like the major piece of the cell. I mean, I would say maybe the OSDs are also a major piece. That's where it's actually stored. But the master is what's kind of making all this happen. It's the coordinator for the cell, and it contains most of the complex protocol logic in the system. Its main job is to watch the OSDs and trigger data repair operations whenever one fails. So this is the thing that if it can't get something, it coordinates the actual, reproduction of the data from the fragments or from the replicated data. It also coordinates background operations, like creating new storage buckets when they get full, triggering garbage collection when data is deleted, or merging buckets together when they become too small after garbage collection. So the master is kind of, coordinating everything, essentially, in the cell. So let's look at some common operations for Magic Pocket and what they might look like in the actual architecture. So here's a put operation, and you can see the first thing that happens is it's a call to put the block. So the first place it goes is the front end, right? That's, again, the interface to the entire Magic Pocket system. The front end first checks if it exists in the block index. And after that, it looks up the volume, and it knows where to look because the block index knows where to look, right? So it goes to the replication table. After that, it writes it to the OSDs. Those are the storage devices where it's actually being stored, which then comes back and maps and updates that block index to say, hey, like we stored it here. This is where you need to remember where it went. So that finally goes back and, the system responds that it's done its job. So again, it's kind of this like conversation between all of these different systems, keeping track of where things are and who has what, because when there's a lot of data and a lot of replication in different places, there has to be some tracking of where things went and, you know, who's who. So that's more or less how this system works. So let's look at one more. This is a get operation. And this is actually, so it's not actually a full, diagram of the operation itself. But in this case, if a block is, A-OK, you can just get it right from the OSD. But if it's not, what can happen is that the master will coordinate all of these other replicated data along with the parity extents. These are those fragments that are created when you erasure code something. And instead of returning just the block, it reconstructs the block from the various places that it's replicated, and it can return it after that. I hope you all enjoyed this video. I really enjoyed making it. I know that this was a pretty specific and intense deep dive into the Dropbox system. And I want to reiterate that the reason we did that, why we wanted to make these videos all about Dropbox's system, is because that the different components that make up the system, and there are a lot of components, clearly, we like barely scratched the surface in these two videos. These different components you can use when you're building a different system for a different system design question. All of these ideas, this like replication idea and the different availability zones and the way a sync engine might work and testability and, talking about the workload of a system, the ways in which Dropbox have solved these problems, a lot of other companies have also used these similar approaches to solve similar problems. And knowing all of these are almost like Lego blocks that you can then take and plug and play, right? You can make a new system from these blocks that we discussed here today in the Dropbox system architecture. So definitely join us next week. We're going to be doing some more amazing, interesting system designs questions. I'm really enjoying these because it's fascinating to kind of understand systems that are all out there and all of the pros and cons of all of these different decisions. And yeah, have a great week and keep learning.